Hello. In this presentation, I will discuss membership inference attacks on large-scale multimodal models like CLIP. Before delving into the main discussion, let's define what a membership inference attack is. The objective of a membership inference attack is to determine whether the data record was part of the training dataset with the help of a data record and access to the model. For the dosage predictor for heart disease, if an attacker can determine whether the target data is used during training, the privacy of the victim will be leaked. So now, why it is important? There are several reasons. First, curiosity. People often want to know if a company used their data. Second, data extraction. Membership inference attacks can serve as a foundation for the data extraction from trained model, making the improved attacks essential for more effective data extraction. Third, editing. Individual might want to edit the accuracy of the privacy algorithm and use these attacks to verify if the attack algorithm is as private as claimed. How has previous work dealt with this attack? The initial approach is based on an attack model, which is a binary classifier to determine the membership inference information. In this method, an attack model is trained through the supervised learning. Then the trained binary classifier is used to determine the membership status of the test data. The challenge here is to acquire training data for the attack model. Many works have utilized shadow model for this purpose. Attackers construct multiple shadow models, using them to create a training dataset for the attack model. This shadow model must be trained similarly to the target model. Another approach is based on metrics. In particular, metric-based membership inference attack makes the membership inference decision for data recorded by first calculating metrics on their prediction vectors. Then the calculated metrics are often then compared with the preset threshold to decide the membership status of the data record. However, these approaches have clear limitation when it comes to large-scale multimodal models. For instance, shadow model training is computationally expensive. Moreover, the full details of training algorithms are often not publicly available. So we propose three attacks. First one is cosine similarity-based attack. This is similar to metric-based attack in traditional membership inference attacks. Since CLIP is trained to maximize the cosine similarity between image and text features, we can leverage the cosine similarity as a metric to determine membership information. For the augmentation enhanced attack, we first apply the data augmentation to the image side and then calculate the cosine similarity with the corresponding text feature. Then we aggregate the gaps between the original cosine similarity and cosine similarities with k number of augmentation. We added these gaps into the original cosine similarity to detect the membership information. For the weakly supervised attack, we assume that we can access the one-sided information about non-members. This assumption is not strong since nowadays GPT multimodal models usually open their publication dates, and we label the data samples scrubbed after the publication date as non-member. We first calculate the cosine similarity for this non-member set. Then we can calculate the mean and variance of this set. Using this mean and variance information from this set, we can identify pseudo-member samples from a noisy set which contain both members and non-members and label them as members. After collecting members and non-member samples, we train a binary classifier to determine membership information states for inference samples. After training the attack model, we use this attack model to decide the membership information for the inference samples. We observed that both the AEA and the WSA enhance the attack performance compared to the simple baseline. In particular, the weakly supervised attack showcased a substantial improvement with a reasonable time. We also found that cosine similarity-based attack cannot correctly identify the non-member samples that received high cosine similarity, but weakly supervised attack can mark it correctly. We also evaluate our attack against several defenses. Data augmentation-based mitigation achieve a better utility privacy trade-off compared to L2 regularization, which compromise zero-sum performance. However, both mitigations are still vulnerable to our proposed attack. Injecting Gaussian noise into prediction can mitigate our attacks, but it requires strong magnitude of the noise. That also decreases zero-sum performance. Thank you.